Thank you. Good morning. My name is Aaron Match. I'm a postdoc working with Ed Gerber at NYU, and this work is done also in collaboration with Stefan Fugler-Staller. His work is on protection without poison, why tropical ozone maximizes in the interior of the atmosphere. So let's have a look at the number density of ozone in the atmosphere, molecules per volume. You can see our ozone layer way up there in the stratosphere. The ozone layer provides protection from ultraviolet light. We can conceive of this protection in terms of optical depth. Optical depth is given by of ozone is given by the total column ozone, which is the vertical integral of this plot. It's about 10 to the 19 molecules per square centimeter, times some absorption coefficient, which is going to be a function of wavelength. The peak absorption coefficients for ozone are about 10 to the minus 17 square centimeters per molecule. This is absorbing in the very high energy wavelengths of ultraviolet C light, which are capable of damaging DNA. So it's very good that ozone absorbs this. This leads to an optical depth of 100. So that means that incoming UV at these wavelengths is attenuated by 100 E foldings. To give a sense of that amount of attenuation, I'm going to compare it to eclipse glasses. Okay, raise your hand if you looked at an eclipse through eclipse glasses in the past year or ever. Yeah, very good. So eclipse glasses actually have a legally mandated optical depth, essentially, and it's a tau equals 10. So ozone is providing the equivalent of 10 eclipse glasses in a row of protection from UV in its wavelengths where it's most strongly absorbing. But it's very fortunate that ozone is high up in the atmosphere, providing us that protection, because ozone is also poisonous. If ozone were well mixed, then it would exceed the EPA safety threshold of 70 parts per billion down at the surface by a factor of 8. So we're fortunate that we have ozone, but that it's far away. And asking a very simple question, why do we have ozone, but why is it far away? Is the topic of this talk. So why does ozone in the tropics, is what I'll be focusing on, have an interior maximum around 26 kilometers. Now, this is a very old question. And there's actually, if you look at textbooks explaining answers to this question, you'll see two common explanations. The more common one, I'm going to refer to as the source-controlled paradigm. It's the idea that the peak in ozone occurs at the peak in the ozone source. And that ozone source is often then argued to maximize at a sweet spot between two curves. It's the photolysis rate of O2. That's basically how many UV photons are still available to photolyze O2 and produce ozone. And that's declining monotonically towards the surface. And the number density of O2, which is increasing exponentially towards the surface. And the product of those curves can have an interior maximum. But there is a well-known problem with this explanation, which is actually the ozone source maximizes about 10 kilometers above the peak in ozone itself. So that's not a small quantitative error, and we want to do better quantitatively. There is a second explanation, which takes into account the sink as well as the source. I'll call it the source-sink competition paradigm. In this argument, peak ozone is argued to result because the photolysis rate of O2, which is producing ozone, drops off much quicker than the photolysis rate of ozone. So in this explanation, there's an explicit role played by the absorption of photons by ozone. This explanation can be made quantitative by invoking the Chapman cycle, the century-old explanation for structure of the ozone layer, and you get a scaling for the shape of the ozone layer, as is noted in most textbook explanations of ozone structure. But as is also noted, the Chapman cycle actually neglects the dominant sinks of ozone in our atmosphere. These are from catalytic cycles and transport. And so what we want is a quantitative theory for peak ozone, which is formulated in terms of its dominant sources and sinks. And so now I'll step through those dominant sources and sinks. So everything starts off in ozone photochemistry when UV photolyzes O2, forming two atomic oxygens. That atomic oxygen can then bond with O2 to form ozone. Once formed, ozone is a very potent absorber of UV. That's the 10 eclipse glasses I referred to earlier. And that breaks the ozone back into O2 plus O. And this reaction number 3 is often followed by reaction number 2, where the atomic oxygen then reforms ozone. And these two reactions cycle back and forth. Each of them conserves what's called odd oxygen, which is O plus O3. and they, in the process, absorbing a huge amount of UV. Now, in the Chapman cycle, the sink of odd oxygen, okay, so the source comes from reaction 1, the sink comes from a fourth reaction, which is O plus O3. But as I mentioned, that sink is actually quite minor in observations. At no altitude is it dominant. And so the approach I'm going to take in this talk is to augment the Chapman cycle with reactions which represent the generalized destruction of ozone from a whole family of sinks that come from catalytic cycles and transport. And these generalized reactions are very simple. The first one is just a reaction which destroys atomic oxygen. And the key to this is going to be calibrating the reaction rate for this reaction in a realistic way based on our knowledge of catalytic cycles. And a second reaction, a destruction of ozone, which I'm going to use to represent the generalized destruction by transport. This is a bit idiosyncratic to represent transport as effectively as a chemical reaction. And what I'm thinking of here is the tropical lower stratosphere, where advection tends to damp ozone. The upwelling of ozone tends to damp it. And so augmenting the Chapman cycle with these two reactions leads to a system of equations we call the Chapman plus 2 model. And we're going to investigate that model. Okay, so these 6 chemical reactions can be algebraically solved for ozone at a given altitude in a steady state. This equation, it's sort of bulky. It's also implicit because it depends on JO2 and JO3, those photolysis rates, which depend on the overhead ozone. So to solve it, you have to integrate from the top of the atmosphere down. But that's not a problem for a computer. So what we're going to do is input the incoming ultraviolet flux as observed at the top of the atmosphere, absorption coefficients of ozone and O2 as measured in lab, and damping rates. These are the rates for reaction that destroy O and ozone, and they're calibrated against the known concentrations of catalysts and the known transport rates. And we validated these damping rates against the results from a comprehensive chemistry model, chemical transport model, by comparing our solid cyan curve with the linear ozone model's dash curve. And the result we get is shown down here. The Chapman plus 2 in magenta, that's tropical ozone profile as compared to an ozone profile for MERA2. It's a good fit, which gives us confidence that we can now use our very simple framework to try to understand ozone structure. And in proceeding to now understand how structure emerges from this Chapman plus 2 model, it is convenient that actually in that bulky denominator, 4 of the terms are never dominant at any altitude. And so there are actually just 2 regimes of this model. The first regime is one in which the damping of atomic oxygen is dominant. You can see kappa O in that term. And when that is the dominant term of the denominator, ozone simplifies to this much simpler expression, which you can see is in terms of JO2 in the numerator and the JO3, the photolysis rate of ozone, in the denominator. We're calling this the O-damped limit. And because it depends on that ratio of JO2 to JO3, this actually reduces exactly to the source sink competition paradigm that comes from the Chapman cycle. And I'll note that the kappa O in today's tropical stratosphere is dominated by NOx. Now, there's another limit to these equations. If kappa O3 is dominant, the damping of ozone, then you end up in the ozone damped limit. And you see that in the ozone damped limit, ozone is scaling as the photolysis rate of O2 times O2. And you've seen that already as well. That's actually exactly the source controlled paradigm. And kappa O3 here in our system is dominated by transport. And so what I'm showing is that these 2 textbook explanations for the shape of the ozone layer actually correspond to well-defined limits of this more generalized Chapman plus 2 photochemistry. And so then the question of understanding the ozone maximum reduces to understanding which of these limits explains the maximum. So let's look at the size of terms in that denominator. Here they are. So the ozone layer is in an O-damped limit above 26 kilometers, as we see by this red term being larger than the blue. There's a transition at 26 kilometers. Below that, ozone is in an ozone damped limit. Now, this transition is at 26 kilometers, but that's actually exactly the maximum of ozone number density. So it's still not obvious how we can use these to understand the interior maximum of ozone. So let's dig a bit deeper. Here again is the ozone profile for MERA 2 in black, our Chapman +2 model in magenta. And the O-damped limit applies above 26 kilometers. And so if we just fit this simpler O-damped limit expression, we plot that in red, you can see that it reproduces the full Chapman +2 solution from magenta. Now down below 26 kilometers, it's in the ozone is in the ozone damped limit, which is reproduced by the blue curve. That's the source controlled paradigm. Now let's see if either of these limits can explain the interior maximum. So let's look at the O-damped limit and artificially extend it across the whole domain. And what you see is that the O-damped limit is trying to predict an interior maximum of ozone, which is 10 kilometers too low, and which occurs in a region where the O-damped limit doesn't actually apply. So the O-damped limit cannot explain the interior maximum of ozone. What about the ozone damped limit? It's predicting ozone that is 10 kilometers, to maximize 10 kilometers too high, and in a limit where it does not apply. And so this has led us to formulate a new theory for the interior maximum of ozone at 26 kilometers. The regime transition paradigm is the idea that ozone peaks at the transition from an O-damped limit aloft, in which ozone is increasing towards the surface, to an ozone damped limit below. In cartoon form, we can see that these two classic textbook ideas, that in the ozone profile goes from a source sink competition paradigm aloft to a source controlled paradigm below, and the maximum happens at that transition. This has implications for the response to perturbations. For understanding those response to perturbations, models are doing this correctly. We want to understand why. And so the source sink competition paradigm in response to an increase in UV light predicts no change, a spectrally uniform increase, predicts no change in ozone. The source controlled paradigm predicts an upward shift of ozone and an increase in the peak ozone. The regime transition paradigm predicts a downward shift and an increase in peak ozone. And if we just double UV in our Chapman +2 model, we see, in fact, a downward shift and an increase in peak ozone. So we think that this can help with intuition. And so we have offered the regime transition paradigm as a new theory for understanding why the ozone layer provides protection without poison. Thank you.
Yes, go ahead.
Great talk, Aaron. I'm guessing you're anticipating this question, but in the future, transport also changes, so that would change the entire distribution of all these species. Have you tried playing around with like different distributions from chemistry climate model or something?
Yeah, so we treat there's transport can affect it in several ways. So one way within the framework is that if you strengthen transport, then you strengthen kappa O3 and you lift that transition altitude. It goes higher. And so ozone will decline in the region of the maximum will shift upwards. Another way that transport can affect it, the one you're referring to, is that it can change where the catalysts are. And we haven't explored that, but it would do that. Yeah.
Cool. Yeah.
That's a dumb question. Can you go back to that vertical profile plot? Yeah, that one. So I'm just curious, just sort of intellectually curious. To what extent does the departure in the the sort of lowermost stratosphere reflect the fact that there's like no tropospheric ozone in this versus actually just there's more complicated stuff in the stratosphere going on?
The departure between the MERA 2 curve and our solutions. Yeah, right. So we have neglected tropospheric chemistry. It's my sense that we can explain the stratospheric maximum without invoking it, but this this strong departure is a consequence of tropospheric chemistry, which we neglected.
Thanks very much, Aaron.